Okay, the next topic or twist in this story, in a sense, is that we are now going to look at loads that are not vertical. In other words, we've been looking to this point at loads that are vertical. Now we are going to consider ones that are not vertical. In this particular case, that load is at an angle of 60 degrees to the horizontal. So how do we handle it? Well, it's pretty straightforward. We are going to use components to represent that 15 kip force. So the way that we're going to do the components, we're going to use create a vertical and horizontal component so that we get all our forces to be either vertical or horizontal. And the way that we're going to do it is the standard way that you've always gotten components. We're going to use a triangle, and the triangle that we're going to use in this particular case, you're familiar with it, is going to look something like this, where 15 is the hypotenuse of the triangle, and the angle there is 60 degrees, so that comes obviously from here. And we want to get the x and y components, and it's just basically using standard geometry. If I look at this triangle here, I see that the sine of 60 degrees is y over 15, which means that y is equal to 15 sine 60 degrees. And the cosine of 60 is equal to x over 15. So that means that x is equal to 15 cosine 60. So now, in terms of the equivalent forces then, what we find is that because of this relationship, we get that this 15 kips at an angle of 60 degrees is exactly the same as 15 sine 60 in the vertical direction and 15 cosine 60 in the horizontal direction. Now, the way that we do it is that we note that both arrowheads, so look at the arrowheads here of these two forces, they are located at the spot of the original arrowhead. So, right there. In other words, we use this to do the calculation, but, we don't leave the arrowheads there. We have to, in other words, these two forces acting at that point are equivalent to this one force acting at that point. I think that you can see that makes some sense. And you learn this in physics, so you just need to apply it here. Now, this is the way that we're always going to do it. So you need to use this. As I said, you're going to use my method. We're always going to use the angle. We're not going to use a ratio or anything like that because engineers use angles. We're going to do things the engineering way, not the mathematician or the physicist way. And so engineers in practice will be using an angle here. And so we're always going to use an angle, and then that makes it easy for us. So in other words, we're always going to do it this way. I need you to learn this, and you got to be able to do this very quickly. And it's quite simple. So the vertical is the hypotenuse times the sine of the angle, and the horizontal is the hypotenuse times the cosine of the angle. That's straightforward. So in the y direction it's sine, and the x direction it's cosine. You need to learn how to do this very quickly. Now the trick is, of course, that you always have to draw your angles with respect to the x-axis. You have to use the x-axis. If you want to use this rule, you have to look at your problem and make your angles with respect to the x-axis. This one is, right? Because there's the x-axis, and it's 60 degrees with respect to the x-axis. So if you have all your angles with respect to the x-axis, then it's going to be the sine of the angle will be the vertical force, and the cosine of the angle will be the horizontal force. So once you do that, then it becomes automatic. It's easy. You don't have to think about it. So the idea here is we don't want to struggle with the simple stuff. So I want you to follow this method. It becomes automatic. You don't have to think about it. So we're not making little mistakes of sine and cosine, and it's easy. I can tell you right now, if you don't follow this method, you're going to get confused and you're going to make mistakes. You follow this method, everything's easy and you don't make mistakes. So that's what we want. We want things to be easy and we want you to not make mistakes. So just follow this method. So, excuse me. So what you have to what you have to recognize is that the shortcut is that we have to think about, the other part of it is that we have to think about the direction of the vector that we're doing. So in other words, I'm looking at this vector, I'm replacing it. Now notice, this vector here goes downward and to the left. So you just look at it, downward to the left. And that means what? That means my two x and y vectors will be downward and to the left. So you can say it out loud to yourself. Oh, this is downward to the left, so I need a downward and I need a to the left. And the vertical one, the downward one, is the sine of the angle. The horizontal one, the one to the left, is cosine of the angle. So it's that straightforward. We'll go through several of these. Okay, so we want to find the reaction. So this is our original problem. Then what do? I now, at this point right here, I put two forces, 15 sine 60 going down, 15 cosine 60 going to the left, all at this point. I'm not going to move. In other words, what students will sometimes do is they want to put one force here and another force over there. Don't do that. They both go at this point. Okay, don't put one of the forces out in here somewhere. That's not where it belongs. It belongs right at the point there. So once I have this, then what? Now I just do, some of the moments about A. So it's going to be, well, I did the numbers here. 15 sine 60 is 13 kips. 15 cosine 60 is 7.5 kips. So, so that we're going to have the sum of the moments about A. What do I have? I'm going to have 15 sine 60 times 3. So that's 13 times 3. Now, how about this one? This one, though, is what? This one, the line of action goes through the point. So that would be 15 cosine 60, or 7.5 kips times 0. So I didn't have to show it, but, that one disappears because it's 0. The line of action goes through point A. Then we have 10 times 8, and we have by times 6, and of course AX goes through the point, so we don't need to use that. And then we have to get the sign, so this is going to be clockwise, so it's positive, counterclockwise, so it's negative, clockwise, so it's positive. I put all those into here, and I get that by is 19.8. I take the sum of the moments about b equals 0, so I'm taking moments about this point. Again, AX goes through the point. The 15 cosine 60 goes through the point, so all those would be 0, so I only need to do the other loads. So this is AY times 6. This is 13 kips times 3. This is 10 times 2. And then the signs are what? That's clockwise, so it's positive. Counterclockwise, it's negative. Clockwise, it's positive. I put all those in here, and I get AY is 3.17. Now we're going to use the sum of the forces in the x direction equals 0. So that's pretty straightforward. I have AX minus 15 cosine 60. So right there, I get AX is equal to 7.5 kips. And there is my final free body diagram. I can check. Upward forces equal downward forces. Forces to the right equals forces to the left. There's a small round off, it's okay. And I'll just mention that in engineering we'll use 3 or 4 significant digits. In other words, we don't use 10 significant digits. And we don't use 1 significant digit. Generally in engineering practice it's 3 or 4 significant digits. So that's what you want to use for the rest of your career. So this is not just in this class, but for the rest of your career, you're going to use 3 or 4 significant digits. Okay, so I want you to work this problem. You've got 2 forces. Now notice that one of the angles is given with respect to the y-axis, not the x-axis. Now, you have to make a correction. In other words, right here, look. That angle is with respect to the y-axis. You don't want to use the angle with respect to the y-axis. You want to use the one with respect to the x-axis. Okay. All right, so pause the video here and do this problem. Okay, so what do we do? Now, this, like I say, this should be automatic. So what do? We first replace these forces here. Well, this force is downward to the right. So that means I know that I'm going to have a downward to the right force. And what are they going to be? Well, the vertical one is going to be 20 sine 50. The horizontal one will be 20 cosine 50. So their values are given here, and there they are. For the other load, what do I see? Well, it's 20 degrees with respect to the y-axis. It means it's 70 degrees with respect to the x-axis, so I'm going to use the 70 degrees. I have to use the angle with respect to the x-axis to use my method. So what do I have? I have 7 sine 70, 7 cosine 70. You can do those right away, easily. And notice it's not 20. I get these values. So this force is what? It goes upward to the right. Upward and to the right. That means I need to have an upward and a to the right. So you have to get the right directions. You have to get the correct directions, or you're going to mess it up. So you have to just say it out loud. Upward to the right. Upward to the right. Then you're not going to make mistakes. So the sine one goes on the vertical. The cosine one goes on the horizontal. So now we're going to work from this free body diagram and take moments about A, and it's going to be what? It's going to be, well, first we're going to note that what? That this goes through the point, this goes through the point, or the line of action goes through the point, so we're not going to consider those. So I'm just going to do the vertical one. So I have 6.58 times 2. I've got by times 5. I've got 15.32 times 8. And the signs are, this one is clockwise, so it's positive. This is counterclockwise, so it's negative. This is clockwise, so it's positive. So I put all those in. I get by is 27.14. Then I'm going to take moments about b. 6.58 times 7. AY times 5. 15.32 times 3. This is clockwise, so it's positive. This is clockwise, so it's positive. This is clockwise, so it's positive. So all of them are positive here. And I get AY is negative 18.4. So when I do my final free body diagram, oh, sorry, I forgot the X. So we take the sum of the force in the X direction equals 0. And I've got that's to the right. So we've taken to the right being positive. So this is to the right, so it's positive. This is to the right, so it's positive. This is to the right, so it's positive. And solve for AY is negative 15.25. So I have to flip it around to go the other way. So that's my final free body diagram here. And the AY has to be reversed, so it's 18.4 going downward. The other one stays the same. And if I look at this, I'm not going to go through it, but I can check it, and I can see that my up force is equal to down forces, my right force is equal to my left forces. This is not a true check here, because that's what we did here. So it's not a real check. The other one is a real check, but this one is a slight check to make sure, there's a little bit of a check on your math and to your drawing. Okay, so I want you to do this one. So this is find the reactions, and go ahead and pause the video and do this one. Okay, so you should be getting quick at this. This is going downward to the left. This is going downward to the right. So I'm going to have downward to the left, downward to the right. Both angles, both of these are with respect to the x-axis, so I can use my method. So this is 7 sine 50, this is 7 cosine 50. This is 4 sine 35, this is 4 cosine 35. And you can see the numbers here. All right, we've done these so many times, I'm not going to review the moments, but I will talk, since this is new, the forces in the x direction. Well, I want you to take to the right as being positive, and so if I look at this, I have AX to the right, that's plus. This goes to the left, so it's minus 4.5. This goes to the right, so it's plus 3.28, and I solve for AX is 1.22, so that's positive. It means I keep it the same. And you could use, difficult to do a check with this method, so I'll accept either one. Either use the components, put the components there in your final free body diagram, or you can do it this way. Either one. But to do your check, you need to use these. It's difficult to do the check of, up equals down when it's like this. You have to do some calculations, but all right. The next topic is distributed loads. How do we handle them? What do I mean by distributed loads? Well, here is an example right here of what we call a distributed load. If I look closely here, we can see that the magnitude is 4 kips per foot. What does that mean? In other words, if I take 1 foot horizontally, so in other words, if this distance is 1 foot, then in that 1 foot, we have 4 kips of force. So for each foot, I have 4 kips of force. And that means that if I have 4 kips per foot and I have 11 feet, then my total load is going to be 4 kips per foot times 11 feet, which is 44 kips. Now, what we're going to do to get the reactions is that we are going to substitute for this distributed load and basically create the 44 kips. So this works for reactions. I can substitute the result, what we call the resultant of that distributed load, at the centroid of this shape. Now this shape is a rectangle. We all know that the centroid, or center of gravity of a rectangle, is at the center of the rectangle. So in this particular case, this is 11 feet. That means it's 5.5 feet from, either the left end or the right end, however you want to measure it. So I'm simply going to take that load of 44 kips and put it here in the center of this rectangle. So that's our substitution. Then what do? We solve for this. We solve that problem. I'm not going to go through it. You can all do this. This is easy. It's very easy, right? So how do we handle a triangular distributed load? So in other words, it looks like this. This is a rectangle. Well, what does this mean, by the way? It's okay, so I label this 10 kips per foot. So notice the similarity in the units here, kips per foot. How do we interpret it? Well, that means approximately in this region over here, I have 10 kips per foot. In other words, if I take a foot over here, that horizontal distance is 1 foot. That means that we're going to have 10 kips in that region, approximately. I mean, there's some issues the way I've drawn it, but no matter. I think you understand the way this picture works. I'm at 0 here. In the middle, I'm at what? I'm at 5 kips per foot. So if I take a section of 1 foot here, in other words, if this distance here is 1 foot, then I have 5 kips in that 1 foot, because in that region it's 5 kips per foot. That's what this little sketch indicates. And then if I get over here, I'm at 0. So it just shows us how the load is distributed, and basically it's, you can see it's going to be half of a rectangle. So, what do? I get the area of this, which of course is 1/2 the base times the height. And in this particular case, the base is 6 feet. The height is 10 kips per foot. So it's 1/2 times 6 feet times 10 kips per foot. And notice the units come out of this as kips. So, which is what we want. So we're basically finding the area of this triangle, and that gives us the load. So 1/2 the base times the height of this rectangle or triangle is 30 kips. Where do I put it? Well, you may or may not have learned, but I'll tell you where the centroid of a triangle is. So I need to find the centroid of that triangle. It's not hard. Other people have done it, but we use what was called the 1/3, 2/3 rule. So 1/3, 2/3. And so it's 1/3 from the large side, 2/3 from the skinny side of this triangle. So in other words, this is the large size, and I go in 1/3 that way. Or this is the skinny side, and I go 2/3 in that way. 2/3 of what? 6. 1/3 of what? 6. So that means that the centroid is located 1/3 from the fat side, and that gives us 1/3 of 6 is 2. So it's at 2 feet. So that's where the load goes. We figured it out to be 30 kips by getting the area. We put it there, 2 feet from the fat end. what students will make a mistake is they'll go 2/3 from this end. Don't go 2/3 from this end. Or sorry, 2/3 from this end is correct. Don't go 1/3 from this end. Do not go 1/3 from that end. Go 2/3 from the skinny end. You want to go 1/3 from the fat end. So don't do it backward is what I'm going to tell you. So that's the 1/3, 2/3 rule. 1/3, 2/3 rule. So need to know this. You need to know the 1/3, 2/3 rule to get the centroid of a right triangle. So this is it in more detail here. How do we handle a trapezoid? What do we do if we have, in this case, 14 kips per foot at that end, 4 kips per foot at the other end? So that means that again, if I look at, in a sense, the last foot on the left here, I'm going to have 4 kips. If I look at the last over here, I'm going to last 1 foot over there, I'm going to have 14 kips. So that's the meaning of the units. And how do we handle this trapezoid? Well, it's pretty easy. I'd break it into a triangle and a rectangle. So I just come in here, cut that off. I get a rectangle here, which we've already dealt with. And then I get a triangle up here, which we've already dealt with. So trapezoids are easy to deal with. We break them up into 2 parts like that. And notice what the units are. I've got to be true to my units. I come across here. That is 4, right? Because it's here. 4. So that's 4 kips per foot. But that also means that the other portion from here to here is 10 kips per foot. So we get 2 pieces here that look like that. One which is a uniform at 4 kips per foot, and the other which is at one end is a 10 kip per foot. So I simply get my area of my rectangle, area of my triangle. And rectangle is base times height. The base is 6, so it's just simply going to be 4 times 6. And the other one is 1/2 the base times the height. So again, the base is 6, is 1/2 of 6. In this case, the height is 10 kips per foot. We end up with 30 kips. And again, where do we put those loads? Well, for the rectangle portion, which was 24 kips, it goes at the center of the rectangle. That's the centroid of the rectangle. So it goes, oops. It goes, 50% in from the left and right, halfway from the left and the right. Whereas the 30 kips goes, it's a triangle for the 30 kips, and that means that we follow the 1/3, 2/3 rule, which means in this particular case we go 1/3 in from the fat side of the triangle. Fat side being here, the skinny side being over here. So 1/3 of the fat side, 1/3 of the distance from the fat side, the total distance is 6, so 1/3 of 6 is 2. So it looks right there. So I simply take, so now I have, there's, my loads, and then I simply draw my free body diagram from that, and get the reactions from from this diagram in a sense. Now here's another example down here. What do I have? I've got 3 feet and 8 feet trapezoid. So what do? I create a rectangle here. I create a triangle here. And this is just another example, which means that what I have, my rectangle is 3 feet, because I'm taking it right here. And that means that that this is going to be 5, oops. This is going to be 5 feet. This is 0 over here. And we can create, again, the area of this one, which is 3 feet times, and the x distance is 9 feet, so that's 27. 3 times 9 is 27. So we got, for the rectangle, 27 kips. For the triangle, I've got 1/2 the base times the height. So it's going to be 1/2 times 9 feet, because that's the base. The height, now I just have to do with the second part of it. I'm not going to go back to, the original of 8. So I get 1/2 the base times the height, where 1/2 of 9 times 5. And so I get 2 different loads. I get to 27 for the rectangle and 22.5 for the triangle. And then when I put them on, we can see that it's a rectangle. So it's only 4.5 feet from the left end, 27 kips. Whereas the triangle, I end up with at 22.5 kips at 3 feet. So that's this. We can now do the reactions using this, using that free body diagram. And like I say, I've done so many of these, I'm not going to do these over again. But again, you can follow this, pause the video and follow it. Okay, homework for you. Do this problem, find the reactions. Pause the video. Okay, I'm going to assume that you have paused it. And you solved this problem. So what do I have? I got 3 times 4, that's 12. Where does it go? In the middle of that. So that means that it's 2 meters from the right end, 2 meters from the left end, and it's simply, 3 times 4. And then this is 1/2 the base times the height. So the base is 3, the height is 10. And we end up with 15 kilonewtons, because 3 times 10 divided by 2 is 15. And where is it located? Well, it's going to be located, It's going to be located closer to the left end, because that's where the tall part of the triangle is. So just to use some common sense. And then it's 2/3, 1/3. So 2 meters from the right, 1 meter from the left, 2/3, 1/3. The x-axis was 3 meters. Again, I'm not going to go through this. Once we have this, we find the reactions. I will let you go through that. And we get our final free body diagram from those reactions that we just found. In other words, we treat this the same way we would treat this, in a sense. But we can see that this is what we can use to do our calculations with. Okay, your project to do here, find the reactions. So I'm going to assume you paused it. So now what do we have? We've got, again, triangles. And if we look at what was given, we were given this 8 for the centerpiece in the triangle, and then we have 6 meters and 9 meters there. So that 1/2 the base times the height of this one comes to 36 meters. Kilonewtons, sorry, kilonewtons. And 1/2 the base times the height of this one is 24 kilonewtons. So in that sense, this is pretty easy, assuming that you know, you got your 1/2 base times the height, so that's pretty straightforward. So again, you have to make sure that what? Here's my skinny end. It's 2/3 from the skinny end, 2/3 from the skinny end. So for this one, it's 9. 2/3 of 9 is 6. There's where my 36 goes. This one's 6. 2/3 of 6 is 4. So that's where that goes. 2/3 from the skinny end from the. So we solve this. Again, I'm not going to go through it because at this point it's sort of trivial. Go ahead and look through this to figure out how we got the AY and BY. Okay, now you need to do this one, so pause the video. Well, again, it's pretty straightforward. Now I'm just going to break this up like this, and a rectangle. And you have to pay attention. This is where people will mess up a little bit in breaking these things up. So I've got a rectangle at 1, so I just come across here. It's 1. But I have the triangle as 2. Why? Because this is 3, so the picture is not that great. But no matter. We have now, this is our equivalent trapezoid. With trapezoids, we always break them into 2, rectangle and triangle. So there's our rectangle, there's our triangle. And the area of the triangle is 6 kilonewtons, and the area of the rectangle is 6 kilonewtons. So a little bit confusing, but where do they go? Well, we already know that it's, like I say, for the triangle, it's the 1/3, 2/3 rule. So we go, you know, this is a total of 6. So 1/3 of 6 is 2. So I go from the left end, I go from the left side here, I go 2 meters. This is the triangle. And the other one is 3 meters from this side over here, because it's 1/2 of 6, 1/2 of 6, and so it's put there. Again, now by now this should be a trivial problem for you to solve, so we solve this one, but our final free body diagram looks like that. Okay. Again, homework, find the reactions. Let's just see. Yeah, okay. So pause the video here. Okay, I'm assuming you did that. Again, what do we have? We've got, this is 60 degrees with respect to the x-axis, so I have 4 sine 60 going down. Oh, and let's think it through. This is downward to the left, so I go downward to the left. And it's going to be 4 sine 60 going down. It's going to be 2 kilonewtons, or 4 cosine 60, 2 kilonewtons going to the left. So downward to the left, it fits. This is a rectangle. This is 4 times 2 is 8. And we put the 8 where? The 8 is going to be in the center of that rectangle, because that's where the centroid is. I'll let you do the rest of this because at this point it's pretty trivial. Another one, pause the video and do this one. Now what do we have to do? We've got to replace this force, we've got to replace these. And these also, of course, they're a little bit more straightforward. So again, we break this down into two parts like this. And so this is 2 at the bottom, and this is 3 at the top. So we end up with our 5. And so our areas for the rectangle, 6 times 2 is 12. 1/2 the base times the height for the triangle. And once we have this, and this is upward to the right. So I have upward to the right. So one of them is 20 sine 60, one of them is 20 cosine 60. So this one's going to be 20 sine 60. And the other one will be 20 cosine 60. And yeah. Okay, so now we're down to this. You can all solve it, so pause the video and look at that solution if you'd like. Another one, pause the video, solve for the reactions. Oops. Again, I don't want to beat this to death, but you need to do them so you feel comfortable with them. So it's going to be, again, this is with respect to the x-axis, so it's downward to the left. So 18 sine of the angle was downward. 18 cosine of the angle is that one. Again, we break this into two parts, the green and the blue. This is going to be 1 times 9 for that one. That means this is 5. So that's going to be 1/2 the base times the height, 1/2 9 times 5, 22.5 kilonewtons. We end up with this free body diagram, initial free body diagram, and then I'm just going to let you look at these and be able to duplicate them, and that's what you have to do. And we draw our final FBD here, and you can see it right there. Okay, I'm going to stop there.